So if we go back to this table then, here's just a summary of what we were talking about. We had the radioactivity in becquerels or in curies when we were talking about there being a lot of these decay events. We had the ionizing energy that was absorbed in grays, and that's a joule per kilogram of tissue, or alternatively, a rad, which is 0.01 joules per kilogram of tissue. We had the amount of tissue damage in sieverts, and that was just taking the grays and multiplying by the relative biological effectiveness of the particular type of radiation, or the REM, which was just a rad, also times the RBE. So one of the things that they tell you is that we use radionuclides in various types of radiation therapy. Here are some popular choices, what type of radiation they are. You'll see there seem to be betas and gammas everywhere, what their half-lives are, and what they are used for. You'll see these half-lives in days. Here's one that's in years, and it's just, what are they being used on? And if you're doing imaging, then there is a different set of nuclides that are used. And they're all using gamma radiation in this case, and you have half-lives in hours, and where they are used in various situations. And what they point out here is that the ideal isotope for the imaging has a half-life that is close to the same amount of time that's required for the procedure, that they will emit gamma rays, but not alpha or beta particles. Now, this point here, where it says it has a half-life close to the time required for the procedure, you can also look at this in a different way. Instead of for something where you're trying to use it for a medical positive outcome, you can also talk about what is particularly bad as far as radiation you're trying to avoid. If you're trying to avoid radiation, even though everybody gets very excited about plutonium and, oh my gosh, it's around forever, it's got, 250,000 years for a half-life, the fact of the matter is that means you personally are not going to be exposed to very much of its decay. If something has a very short half-life, you can just put it in a lead box somewhere and walk away from it until it's done. So a very short half-life and a very long half-life are not nearly as threatening to you personally as something that has a half-life that is measured in terms of significant amounts of your life. Something that has a half-life of 10 years was like maximally awful because it's on the order of your own personal lifetime. So you would, if you were in contact with it, you would end up being irradiated by its entire possible dosage. Like I said, if it's a short half-life, you can just put it away somewhere and let it get it out of its system. If it's a really long half-life, it's not emitting very quickly. So this bullet point is kind of interesting in that way. And then, of course, here's another one. It says positron emission tomography. Anyway, you can say, these, we were talking about alphas and betas and gammas, and here we're talking about positron emitting radionuclides. And then when the positrons hit an electron, gamma rays will be emitted, and that's what you're detecting when you're trying to find those. And that's the end of the chapter.